rates of reaction. And like the previous video, this is going to be looking at different types of questions for rates of reaction, but it's going to take a deeper dive in ideal gas law, as well as when we look at reactions where the reactants are in numerous amounts colliding with one another, and there's not many products that have been formed, as opposed to where the products have been formed and there's less reactants reacting in the reaction. So we're going to be looking at those two. But first, let's look at this question. As you can see in this question, we have a mass of 0.50 grams of sodium metal reacts with water in 90 seconds. So the reaction time is 90 seconds. But the problem is I don't want to be using grams, because in chemistry we always want to be using moles. So I'm just going to quickly change my grams of my Na into my moles of Na. Okay, so I'm just, technically there's always an indivisible one at the bottom. So whenever I have two fractions, right, then I can just cancel out whatever the same unit is or same number is, as long as it's diagonal. So I'm just going to be putting my grams on the bottom. That way my grams cancel out, because I don't want it, and I absolutely want my moles, because we always want to be dealing with moles. So I have 22.99 grams per mole of Na. You can find this on the periodic table. So this grams cancels out. So then we end up just getting a value of 0.0217. 0.0217. Okay, and this is moles of my Na. And again, this all happens in 90 seconds time. So I'm just going to divide this all by 90 seconds. But what does the question say? It says express the rate of consumption of Na in moles. Thankfully, I've already done the moles, and it says in per seconds. Right now, this is in 90 seconds. So I just got to divide them. So what do I get? I end up getting 2.4165 times 10 to the negative 4. And then this is moles of Na. And this is all happening in 1 second. That's the answer to that. Now we're going to do B. Calculate the rate at which H2 is generated in liters per second. Okay, so I don't have liters anywhere here. I gotta find it somewhere. Okay, thankfully I did it already in per second, so I'm done that. Next, at 30 degrees Celsius. Ooh, and at 102.4 kPa. Where do these come from? Well, right after that it says assume that hydrogen is an ideal gas. So we gotta figure out what the heck this ideal gas is. We're gonna look at something called the ideal gas law, but to build up to that, I'm gonna be looking at different laws that builds up to it. So we have our first law we're going to look at is Boyle's law. Now, what does Boyle's law mean? It means that our pressure is actually going to be indirectly proportional, so inversely proportional to the actual volume. So whenever we deal with proportionality, you should already know this. We're just going to be putting them over each other. This is not going to be proportional, so we're just going to put them multiplied by each other. So if we have P1 V1 over here, we need to have a second pressure and a second volume on the other side. Now let me prove to you why this would still work, because it's not going to be proportional. So let's have a look here. If this is 100, I'm not going to be putting the units, so it could be kPa, torr, bar, doesn't matter. But just give a discrete number here as 100 for example purposes. And then for a volume, let's say 1. If my volume decreases by half, so now it's at 0.5, what do you think is going to happen to my pressure? Do you think my pressure is going to stay at 100? Or do you think it's going to go lower? Or do you think it's going to go higher? Well, this as a product is 100. So that means this here also needs to be conserved, also needs to be 100. So what times 0.5 is going to give us 100? So obviously going to be 200. So here is going to be 200. So as you can see, my pressure, when I decreased my volume by half, look what happened to the pressure. It went from 100 to 200. So they were pretty much double, right? So this got halved, but this one doubled. So this is why this P1 V1 is equal to P2 V2 is correct, because they're not proportional. Now I've written Boyle's law here on the side. Now let's look at another law. So let's look at Charles' law. Now Charles' law is going to be a little bit different, because if we look at Charles' law, we have proportionality, where now instead of dealing with pressure, we're going to be dealing with volume and temperature. So it's actually going to be proportional. So I'm going to be putting them, dividing each other, as opposed to here where we multiply them, right? Because this is obviously proportional. This one's not. So V1 over T1, oops, sorry, I meant to say T1, okay, is equal to V2 over T2. How can we prove this? Well, if we have, let's say, a container here, and then I have a certain amount of volume, okay, and let's say this container is a little bit bigger, okay, let's say it's that big, and then you increase its temperature with fire, let's say, okay, it's heating it up. What do you think is going to happen to the volume? Well, obviously the volume is going to increase, right? All of these moles of the gas is going to increase. It's going to take up more space. It's going to increase the volume. So of course it makes sense. Whereas the previous example with our pressure and the volume, it's kind of the opposite, right? If you look at a little cylinder over here, and you have a lot of gas particles here, and let's say instead of pushing it down from here, okay, pushing it downwards this way, let's say you started pushing it all the way down, okay, a lot more, so all the way to maybe like half, so maybe about like here, okay? So we've pushed it half here as opposed to just up here. Of course, we've pushed it down so much, halfway down, that all of this gas over here are now trapped in here. So now we have a lot of gas in here that is going to be compacted, okay? All of this gas that's going to be compacted and squeezed and compressed in that small little area. So of course, pressure is going to increase. So we've decreased the volume, but our pressure has increased. This is the exact opposite of what's happening here, right? With our temperature, if there's an increase in temperature, the volume also increases as well. So this is why this here makes sense, where we have them dividing each other, because they're proportional. Next, let's look at Gay-Lussac's law. Okay, you can put a dash in there if you want, doesn't matter. Okay, just looking at the concept. The Gay-Lussac's law, instead of volume and temperature, now we're looking at pressure and temperature. And guess what? They are proportional. So I can make it look like that. They're proportional, so they're dividing each other. So the same thing here happens with a T2. Okay? And this is quite similar as well. If you increase, so we have some gas over here, we increase our temperature, what's going to happen? Okay? Obviously, the pressure is going to increase. So just like volume, the pressure is going to increase with this added increase of temperature, which makes sense, right? Because there's more collisions going around and there's more excited due to the increase of kinetic energy thanks to the heat. Of course, the pressure is going to increase. So this here is going to be our next law. Now we can just combine all of these. I'm just going to put here, this is now going to be the combined gas law, where we have our P1, V1. I'm just going to be putting it beside each other, okay? But what else is going to be combined? Well, we have T1 here and T1 here. They're both on the bottom, so we can just kind of put it here on the bottom. And obviously, the same thing has to happen on the other side, so P2, V2 over T2. This here is our combined gas law. However, we are not done. We still have to add Avogadro's law. I'm just going to put this here on the side. Now here we have Avogadro's law, and it's going to state that the moles is actually going to be proportional to the amount of volume. Okay, why is this the case? Well, let's have a look at the picture on the side. As we can see here, we have a certain amount of volume, 22.4, 22.4, 22.4. They're all 22.4. Okay, as long as the volume remains constant, and same thing with the pressure, and same thing with the temperature, guess what? Regardless of whatever volume you have, it's always going to result in the same quantity, the same amount of moles of that particular gas. So if we're looking at neon over here, it doesn't matter that it has a 40 grams versus oxygen, which is 32 grams. It doesn't matter. As long as they have the same volume, provided that these here, the pressure and temperature are constant, right? This volume and this volume, you see how they're exactly the same, 22.4 and 22.4? They're both therefore going to have the same amount of moles, the same quantity of moles, regardless of whatever this mass is. Same thing can be said for the CO2, 22.4, same thing, 1 mole. Even though we're dealing with a compound here, not even a diatomic molecule, not even an element, a compound here, and has 28 grams, right? Very different than these two. Doesn't matter because it has the same amount of volume, provided that these are constant, that is always still going to be the same quantity of the amount of moles. So what we're going to say for our little equation, that our volume is going to be proportional to the amount of moles. And obviously it's going to be the same thing for V2, for N2. So we're just going to add this here on the side as well. So this means if we put all of this together, I know we already had our combined gas law here, P1, V1, and T1, but we can also add our N1 as well. So we're going to add that over here. And obviously this is going to equal to P2, V2, T2, N2. However, this means that they are acting ideally at a certain amount of temperature. Okay, so for the pressure, it's going to be a certain temperature. The pressure is always going to be at 101.325, ideally. And we're going to put this in kilopascals. I want to work in kilopascals. You can work with another one, okay, like ATM or bar or torr, but I want to stick with the kPa. And for volume, okay, it's going to be 22.4 liters, like we looked at that balloon example. And then we're also going to look at our temperature. Our temperature is actually going to be 273.15 Kelvin. And then for our moles, like we looked at, again, same thing on the balloon example, it was just 1 mole. So if all of these are going to act ideally, we have to have something that's called the ideal gas constant, something that levels all of these kind of together, so that we can just assume when we look at a question like this that a element is going to act ideally. We have to input that into the equation. So we're going to make all of this, or this one doesn't matter. Okay, we can just kind of make a general, instead of P1V1 or P2V2, we're just going to put P and V over T1 and over T and N, and it's just going to equal R. This is going to ideal gas constant, because we want to add and make sure that all of these are taken into account. So R is going to be that value that we're going to be using now. So now we're going to look at our formula down here, right? Our R is equal to PV over NT. And I want you to look at how we're going to be looking at an actual value rather than just letters. So again, we had our R is going to equal our pressure, which was 101.325 kilopascals. So we're just going to multiply that by our volume. Our volume one was 22.4 liters, all over the amount of moles, which was just 1 mole, and the temperature 273.15 Kelvin. So just do a little divisions and your multiplications. What do you get? You should end up getting a number close to 8.314 kilopascals liters divided by moles times Kelvin. So this here is a value that we're always going to be using as a standard for our ideal gas constant. So I'll put this over here on the side. This means if we get our R value over here, I'm just going to write this out again, and I'm just going to rearrange it so that we have this into our more common or familiar formula that you've used to seeing before, is PV is equal to nRT. I'm just going to be putting NT on the side here. So if this right side multiplies by NT, I have to multiply the left side by NT. So this and this, they cancel out. So I end up getting PV is equal to nRT, or NT times R. It's the same thing, okay? But we're probably used to seeing it as nRT. So we're going to be using this little formula that we have here. Okay, so I'm just going to flip this around. Doesn't really matter how you do it. So I'm just going to be PV is equal to nRT. And the first pressure that we're going to be using in this question is 102.4 kilopascals. And then I have to multiply by my volume. Okay, do I have my volume? I don't have any volume here, so I'm just going to leave it isolated. We don't know what it is. And then I'm going to look for my moles. Do I have my moles? Well, unfortunately, our moles for our Na here are given, right, per second. And again, this is all in liters per second anyway, so thankfully we have it in seconds here. So I can already just kind of look more so at my moles, because my seconds are already covered here. I just got to focus on my moles right now because the question is asking for moles. Well, I have it at 2.4165 times 10 to the negative 4, but this is for my Na. I need it for my what? My H2. So I'm just going to go up here. I'm just going to draw it here on the side first. So I have my 2.4165 moles. Okay, sorry, 2.4165 times 10 to the negative 4 moles, okay, of our Na. But remember, this is all per second, and like I said in the last video, divide it by your coefficient, okay, in the denominator. The coefficient that I have for my Na is going to be 2. Well, what am I trying to look for? I'm trying to look for my H2, so I'm always going to make it equal to that. I'm going to be putting H2 over here. Now, I have no unit here on the bottom, so I'll just put an invisible 1 like always, and I'll have to divide it by my denominator. Okay, what is going to be my denominator? My coefficient. Do I have a coefficient in front of my H2? I only have 1, an invisible 1, so I'm just going to be putting 1 over here. So I'm just going to cross multiply these. So I'm just getting 2 times H2 is equal to whatever this value is over here. So we get 2.4165 times 10 to the negative 4. Okay, this is in moles. Okay, and again per second. But I'm just multiplying by 1, so nothing really happens. So this divides by 2, this divides by 2, so this cancels out. So I end up getting H2 is equal to this value, just divided. I end up getting 1.208 times 10 to the negative 4 and this is also all in moles, and this all happens in per second. Now, this is looking for it in seconds anyway, so I've already done it in per second, so I can just kind of ignore this. I just care about the moles right now that I want to extract. So I have this many moles. I'm just going to add this one over here. Alright, so that's how much I have for my moles. Now I need to find my R. Well, I already know what my R value is. Okay, I've already written it down here on the side. So my R value is always going to be, ideally, 8.314 kVA by liter per mole by Kelvin. Okay, but how about my temperature? Do they give us our temperature? Yes, they do, 30 degrees. The problem is, this is in degrees Celsius. I want it in Kelvin because, as we can see, we have a Kelvin here. This Kelvin eventually needs to cancel out, because what do I want at the end? I obviously want my liters, because I'm looking for my volume. So eventually this kPa has got to cancel out. Eventually my moles needs to cancel out over here, so it's going to cancel out with that. How about my K? It's not there. I got to change this degrees Celsius into the K. So if I have 30 degrees Celsius, how many kelvins do I have? Well, in order for me to get this, I want to know what my standard is. My standard, you should already be aware of this, is that negative 273.15 degrees Celsius is actually equal to 0 Kelvin. So how can I make this into this? Well, I have negative 273.15, and I have to add by something to equal 30. How can I do this? Well, to isolate for my question mark, I just have to put this on this side, right? So instead of negative 273, it becomes plus 273. So I just do 30 plus 273.15, so I get 303.15. So if I add this side by 303.15, because I want to get from here to here, guess what? I also need to add this side by 303.15 to get to there. So I just do 0 plus 303.15 to get there. That's just going to be 303.5, so I end up just getting in the here 303.15. So that's how many kelvins. So I'm just going to be putting this in my kelvins, 303.15. There we go. So this cancels out, this cancels out, this cancels out, this cancels out. So I end up just getting my value of 102.4 kPa times my volume, and it's going to equal my 1.208 times 10 to the negative 4 multiplied by 8.314 kPa multiplied by my liters times my 303.15. There we go. So again, my volume here is not alone. I want to make it alone. Right now it's stuck with by multiplying 102.4. What's the opposite of multiplying 102.4? It's divide by 102.4. That way this and this cancels out. If I do it on the left side, I need to do it on the right side here. So I'm going to do it here too. That way this and this cancels out. And then I'm pretty much done. So I'm going to get my volume. I'm just going to multiply them together. I end up getting a value of 2.97 times 10 to the negative 3. Okay, and this is all going to be in liters. What is the question asking for? Calculate the rate at which generated in liters per second. Well, this is all in liters. And of course, I did it in seconds, right? Because I changed my beginning rate of consumption for my sodium into seconds. And then I converted that into H2, which was also into seconds. I didn't change that. So if I put this back into this equation here, it's all under the assumption it's been done in 1 second. So technically, this is liters in that second. So this here would be my answer. All right, let's look at this question. The data in the table below were obtained for the following reactions. Now, we have a certain amount of time, and we have this much HBr. What is the average rate of consumption of HBr over 50 seconds? Well, this should be quite simple in the previous video. If you haven't looked at that video, please look at that for the rates of reaction. So the rate, the average rate, I'll put this here as average rate. Average rate is going to be the difference in the concentration in the numerator. So this here is my concentration. So I have 0.26 in the beginning, and then it becomes, it was 0.42, and then it becomes 0.26. And then I'm going to be dividing it by my 50 seconds minus my 0 seconds. And again, both of these are going to be in moles per liter, okay? So this is in moles per liter, and then this is also in moles per liter, okay? So now, of course, I'm just going to be subtracting them, and I get negative 0.16. This is in moles per liter, okay? And then this here, 50 minus 0 is just going to give us 50, so this is going to be in 50 seconds. Okay, so this is how much average rate of consumption occurred at the end of the 50-second time frame. Okay, so this concentration has been consumed by this much, okay, in this certain amount of time. Now, the question after that, however, is asking what is the molar concentration of Br2 at t is equal to 50 seconds? Well, if this is what happened in 50 seconds, right, because in the beginning it was at 0 seconds, and then at a certain amount per second, there was a certain amount of concentration that was consumed, right? So if I were to actually change this here and just divided them, right, so then I only have a certain amount of concentration per second that was consumed. So I can just do negative 0.16 divided by 50. I ended up getting negative 3.2 times 10 to the negative 3. So that means this concentration was being consumed for every second, okay, from 0 all the way to 50. But at the 50th mark, at the very, very end, we ended up just getting 0.16 moles per liter. So technically, I don't really need this value here. I want this one because the next question is asking for at T50. Even though this is technically what happened over the 50-second time frame, it ended at the 50 seconds, which means this is pretty much what I got at the very, very end. I have nothing else to work with. So this here is what I'm going to be using. So I have 0.16 moles per liter. Okay, for every 50 seconds has passed. So at the end of this 50-second time, right, this is what I have. Okay, and again, like in the previous video, like I said, it's always going to be in a positive value. So you just have to know that this positive value, okay, you have to have it in the back of your mind that this is being consumed. Okay, I'm not going to be putting a negative. Just know that this is going to be consumed. Okay, so technically it is a negative. You just don't see it there. Next, what is the molar concentration of Br2? Okay, so technically this here is for my HBr. Okay, remember, whenever we want to make it equal to find another compound or another element in the chemical equation, I just have to make them equal each other. So here, this is my HBr. I want to make it equal to my Br2 because that's what I want to try to find. And we always want to divide by a denominator that is going to be the coefficient. So the coefficient in our case for the HBr, right, in the chemical equation is 4, so I'm just going to be putting 4 over here. For my Br2, technically it's all over 1, so I'll just draw that there. But the real denominator, the coefficient for Br2, what is it? It's a 2, so I'm going to have to put a 2 over here. So I'm just going to now isolate for my Br2, so I'm going to cross multiply. So I end up getting 4 times Br2 is equal to this, 0.16 moles per liter, and this happens in 50 seconds. But I need to multiply this all by 2 because this is multiplying here by 2. So multiply by 2. Okay, so I'm just going to divide this by 4. So then I divide this by 4. So technically this just is just 2 over 4 or 1 over 2. So again, my Br2 is equal to this multiplied by that. What answer do you get? I end up getting 0.08 moles per liter for every 50 seconds. So this is pretty much going to be my answer. At the end of the 50 seconds, as you can see here, 50 seconds has passed. At the very, very end, what is my concentration? It is 0.08. So this here is my answer. Our next question, over a period of 1.80 minutes, and I can already see here a problem. It says it here in minutes, but over here, I have it in seconds. So I want to quickly change my minutes to seconds because it's going to make my life a little bit easier in the beginning. So instead of 1.80 minutes, I'm going to change it into seconds. Remember, this is technically all over 1, okay? So I'm just going to multiply by a fraction whenever I'm in doubt, and I just want to get rid of my minutes because I want to find it in seconds. So my minutes here obviously have to cancel out, okay? So these cancel out, but then remember, they have to be equivalent up here. So if I have every minute over here, how many seconds? I have 60 seconds, so I'm just going to multiply them, right? So I'm going to 1.80 times 160, what do I get? I get 108. So I get 108 seconds. All right, so this one we're dealing with. Now, the average rate of formation of NO is 1.04. Okay, so I'm going to be putting this here, 1.04, okay, moles per liter, okay, per second. Now, this is happening at 108 seconds because at the end of it, that's pretty much what I really care about because at the end, it says over this period of time. So rather than 108 seconds up here and just 1 second here, I'm just going to multiply them. That way I can figure out what my moles per liter is actually a value of 112.32 moles per liter. So this is my concentration, okay? But again, this is all to do with my NO, right? As we can see over here. The question is asking for moles of O2. So how do I do this? I'm just going to bring this up here. This is again my NO. So I'm going to be putting my 112.32 moles per liter of the NO. And I need to do this for my O2. Again, I'm just going to make it equal to the O2, and technically everything's over 1 by itself. But we have to put our NO dividing by its coefficient, which is a 4. How about for O2? As you can see here, it's a 5. So I'm going to divide it by a 5. So technically I just cross multiply, and then let's see what I get. So I get 4 times O2 is equal to 112.32 moles per liter times 5. Now what I'm going to do? Well, this O2 here is stuck with this times 4. What's the opposite of times 4? It's divide by 4. If I do it on the left, I need to do it on the right. So I'm going to divide it by 4 here on the right. So again, my O2 is equal to this times 5 over 4. What do I get? I'm getting a value of 140.4. Again, this is all 140.4 moles per liter. What is the question asking for? What is the amount in moles of O2 consumed over this time period? Okay, well, the amount of moles, as you can see here, is 140.4. Okay, I know we have liters here on the bottom, but the question is just asking for the moles. So technically the answer would just be what I want over here, 140.4 moles. This here is the answer. Now before we get into our green question of the day for you to try yourself, I want to show you the deal with the reactants and the products and the amount of collision that's going to be occurring during reactants of a lot of reaction and when the products are formed and there's not many reactants left over. In the beginning, lots of reactants are going to be colliding with each other. There's going to be a lot of excitement, a lot of energy, and then they're eventually going to turn into the products. But in the beginning, before they become the products, they're all kind of stuck over here. So in the beginning, it's going to be a very, very large amount, okay? And then eventually, it's going to go to the product side, right? Hence why we have the yield symbol here. This amount is going to go down, so maybe it's only this big right now, okay? So it's not much, because our products, instead of having nothing here, now it's slowly building up, okay? And then eventually, so it's not like this anymore, okay? And eventually, when this amount of reactants keeps going towards the products, what's going to happen to this? This is also not going to be the same. It's going to start getting even smaller, okay, like that. So what's going to happen to our products? Okay, they've got to go somewhere. It's got to go over here. So instead of this, now it's going to be a little bit bigger, okay? So as you can see, the amount of reactions in the beginning is going to be a lot more plentiful, a lot more rate of reaction, a lot more collisions, because there's all packed into here, packed into this room, packed into this party. Eventually, when they start leaving the party and then become a product, there's less over here, and now we're starting to get more over here. For this question over here, which is a green question of the day, please give this a try. Pause the video, try with your best, and I'm going to be showing you the answers shortly. This here is the answer.